All right, we are looking at continuing our discussions on collision theory and how we can impact our rate of reaction. So this is not ideal. My stylist is at school, so I'm going to talk you through a note that I wrote last year. It's going to look really similar to what we wrote yesterday. You are just going to need to pause and copy down what you see and then listen to the explanation. So yesterday we talked about collision theory and how in order for collision to be effective, your particles have to collide. They need to collide in the correct orientation, which is called collision geometry, like we see here, and that they have to collide with enough energy to break apart the bonds and reactants and form the bonds in the products. So the amount of energy, the minimum amount of energy that is needed for a reaction to occur is called the activation energy. We know this already. We talked about the energy potential diagram that looks like this, an activated complex in a transition state, and the activation energy is the amount of energy in between the reactants and the activated complex. We also kind of said that in order, we want to influence, we're going to talk about this. Then we looked at a Maxwell-Boltzmann distribution, and this is going to become important as we move through the rest of this lesson because the Maxwell-Boltzmann distribution is showing us the particles that meet the requirements for a reaction. So the majority of the particles don't have the required amount of energy to undergo a reaction. So that means that the collision is ineffective. So then we left yesterday, we restarted talking about our factors that are affecting reaction rate, and that there are 5 basic factors that we can control the speed of a chemical reaction. So if we wanted to increase the rate of a reaction, we can increase the number of effective collisions. So the first one that we talked about was our chemical nature of reactants. We talked about our activity series. I demonstrated the alkali metals. So those are just elements that are simply more reactive than others. Potassium was much more reactive than lithium. And then some molecules, they have weaker bonds, so they have a lower activation energy compared to those with a stronger bond. And then we left saying that substances are, that's not what I wanted to do. Substances are less reactive, complicated molecular substances are less reactive than simpler mono or diatomic molecules, simply because there's more bonds that need to be broken. All right, so this is new. So the second factor is concentration. If you have a higher concentration of reactants, it's going to lead to a faster reaction. This is because when there is a higher concentration, there are more particles available for collisions. When you have more particles available for collisions, you're going to get an increase in collisions, which is going to lead to an increase in reaction rate. So hit pause and copy that down. All right, so that's very straightforward. Our next factor is when we add a catalyst. So a catalyst is a substance that alters the rate of reaction without being consumed. It's a substance that when you add it to a reaction, it makes it go faster, but when the reaction is over, the catalyst remains in the same way that it was. So our catalyst provides an alternative pathway for a reaction that has a lower activation energy. So because it lowers the activation energy, more particles have sufficient energy to react. So it looks like this. So if we draw a potential energy diagram, This looks very similar to the one that we drew earlier in this lesson together yesterday. We have our reactants, we have our products, we have that pathway that is showing our normal activation energy in green. But if you add a catalyst, it lowers the activation energy, which we see in pink. The orange is an alternate pathway. So the orange is an alternate pathway from the reactants to the products that the catalyst provides. And this alternate pathway requires less energy. So hit pause and copy this. When we look at what happens when we decrease the activation energy on a Maxwell-Boltzmann distribution, it looks like this. So I would hit pause and copy this and then listen to the explanation. So the Maxwell-Boltzmann distribution for when you add a catalyst. Now our original normal activation energy is shown in green. And the number of particles with enough energy with no catalyst is highlighted in pink. But when you have less energy, when you have a lower activation energy, so shown here with the purple, now there's more particles under that curve. So now everything highlighted in blue, that is the number of particles with enough energy when the catalyst is present. So adding a catalyst causes more collisions to be effective because the collisions require less energy. So there needs to be less energy, or the energy requirement is lower in the presence of this catalyst. And so because the energy requirement is lower, more particles meet the energy requirement and more collisions are effective and the reaction rate will increase. Our fourth method is surface area. So the amount of exposed surface area affects a reaction rate. Increasing the surface area of reactants increases a reaction rate as more particles are available for a collision. And I'm going to demonstrate this to you in class tomorrow. So the higher the surface area, the more collisions can happen and the reaction rate will increase. So pause and copy that down. So a good example of how surface area can increase the rate of reaction, you think about that you want to light a campfire and you have like some larger pieces of wood. The way to get the fire to light is to use smaller pieces of like kindling or like wood shavings or sawdust because they have a significantly larger amount of surface area for its size compared to a very large piece of wood. So those small pieces with the larger surface area light first because the reaction rate has increased. All right, our fifth factor to increase reaction is looking at temperature. So if you increase the temperature, you're going to increase the reaction rate. This is because as the temperature increases, the kinetic energy increases. And this results in more particles meeting the activation energy. If more particles meet the activation energy, we get more collisions occurring and more collisions are effective. So pause and copy this. So the temperature increases, resulting in more kinetic energy. So the particles, kinetic energy, remember, is the energy of motion. So the particles are moving around faster. They're moving around faster. They have more of them can meet the activation energy. And they're also all moving around faster, so they're more likely to collide. It's like driving a car. The faster you're driving, the more likely it is you're going to get into a collision. So we look at a Maxwell-Boltzmann distribution for this. So this one right here, we have a temperature of 25 degrees Celsius. Our particles, our energy, this is our activation energy. And again, all the pink is number of particles that meet the energy need. If you have a temperature of 30 degrees, so just a small temperature change, the activation energy moves over here. And now all of this area that's orange, all of those particles meet the energy needs. So a very small increase in temperature can significantly increase the number of particles with enough energy to react. So a 5 to 10 degree temperature change can double or triple the reaction rate. So make sure you have this down. All right, so those are our 5 factors that are going to influence rate of reaction. So what you changed in your lab is going to reflect one of these factors. Chemical nature of reactant, you all used elk seltzer, so that's not going to do anything. Amount of something, crushing it up, increasing the temperature, so when you're thinking about amount, what you're doing is probably impacting concentration. So I think you need to think that way for that. On the slide deck where this video is posted, I'm going to have some questions for you to answer to practice applying collision theory. When you are done those, you can work on either of your labs. And tomorrow in class, we will talk about the reaction mechanism a little bit. This reaction mechanism note that you've done in the past, you did last week, should make a lot more sense now, okay? Because it talks about potential energy diagrams for multi-step reactions. So that should make a little bit more sense, but I'm going to review it with you in class tomorrow. You will also probably have a little bit of time to work on your labs and prepare for your test that is on Friday.